Okay, folks, let's settle back in for the second half of our morning. We have two more talks before lunch. I'm gonna get us started here with Alan Tennant, professor of physics and material science and engineering at UT, who's going to tell us about the experimental side of quantum spin liquids. Thanks, Alan.
Okay, so thanks very much, Michael, and thanks for the invite to talk here. So one thing is we're going to be doing the neutron tutorial this afternoon, which some of you will be attending. So one thing is there was an email sent around that you need to do a registration for the computer account that we'll be using tomorrow as well and next week. Okay, I'm going to follow on from what Gabor discussed and talk about the how we do experiments on quantum spin liquids. I should start off by saying experiments in quantum spin liquids are really challenging. So a lot of what Gabor showed is invisible to local probes, right? So most of what you heard about with this topological quantum effects are something we can't directly access. Some other things like fractional excitations we can see. So experiment is not easy. We have to combine very advanced modeling along with very advanced experimental techniques to address these states. So experimentally investigating quantum spin liquids involves a lot of innovation. We're having to invent approaches to actually meet the challenges of it. But where do we get them from in the first place? So actually a lot of the materials that we have around us in our everyday lives are in fact magnetic, but they're not ferromagnetic, they're anti-ferromagnetic, so we don't notice the magnetism because they involve spins that are anti-aligning rather than aligning. And also the magnetic correlations tend to build up at low temperatures as well. So in fact, there's a vast array of solid-state chemistries and materials that actually provide us with actually very idealized magnets. And in the case where we have low spins, like spin 1/2s, and reduced dimensionalities or large amounts of frustration in the spin networks, we can get quantum effects. So we can actually get close to real model systems. So where do we get the magnetism in the first place from? It's from actually unpaired electrons on transition metals or rare earth ions. And these will, in our case, we're interested in the kinds of ones that are magnetic insulators. So where these magnetic moments on the magnetically active ions will talk to each other through covalent bonds with, say, an intervening oxygen or some other ligand. And so essentially you'll get a bit of overlap of the wave functions, and the spins will, for them to be able to move on to these ligands for short periods of time, will actually anti-align, giving us antiferromagnetism. Of course, there are a vast array of crystal structures out there, plus single ion properties that allow us to get all kinds of magnetic networks at the atomic scale. And, square lattices, triangular lattices, Kagome lattices, and so on, with a whole range of not only quantum spin numbers that we get from the different chemistries, but also anisotropies and so on. So there's a vast chemistry that we're actually only beginning to explore out there. And, in a way, the art form is to, on the experimental side, is to understand what we're seeing in these, but also to make very informed moves towards finding the right states of matter out there. And that takes big teams. It takes teams in materials, expertise in materials and synthesis, different experimental techniques, interaction with theory, and actually pushing the modeling and measurement technologies. So one of the key approaches we have is neutron scattering. This laboratory is actually where neutron scattering started, and it's world famous for it. Neutron scattering is an extremely expensive technique. It's a rare technique, but it's supremely powerful for looking at quantum magnetic effects in materials. Why? Because the scattering of neutrons from magnetic materials has a scattering cross-section which is linear with respect to this quantity at S of Q and omega. Right? S of Q and omega is Fourier transform of the spin-spin correlations in space and time in the material. It's the closest thing we'll get to measuring a wave function in experiment. It's an extremely rich data set that tells us a lot intuitively about what, in fact, the system is doing. So that's one of our key techniques, is using neutron scattering to give us deep insight directly into the quantum states and behavior. It is a local probe. That neutron is going to scatter off a spin in the material, and it is going to measure the spin-spin correlation essentially by doing by probing a quantum mechanically in space and time. But ultimately, the actual interaction with the material is a local interaction. And that's what means that we can't see everything. We can't see topological entanglement, for example, with this technique, but we can see nearly everything else. We have other techniques as well. The main techniques we use, two that really stand out are magnetic susceptibility, magnetization, where we're putting these materials under really high magnetic fields, then often at millikelvin temperatures. We have to work at millikelvin temperatures to get the coherent quantum states forming. So magnetic susceptibility is very important because it can see the magnetic phase transitions. It gives us a map where interesting areas are. And we can do certain tricks as well to learn about what the couplings in the materials are. Heat capacity is another very important technique. Heat capacity allows us to kind of probe the density states in the Hilbert space in the material. So, for example, that can be very powerful for quantum spin liquids. So at lowest temperatures, a heat capacity upon temperature will be proportional to temperature to a power. That's one of the signatures of quantum spin liquid behavior. There's actually a really good paper, if you wish to read it, on that's accessible for experimentalists to also look at measurable quantities, and that's one by Johannes Knoll and Roderick Mosen, our Field Guide to Spin Liquids. That's a really nice article to look through as background. Okay, now I'm going to start working through kind of in the same order that Gabor went through and try and relate experimental techniques and how we do it to that. So in many ways, the kind of the central model in many-body quantum mechanics is the Heisenberg model. It's the one that Heisenberg proposed back in 1928. Bethe put forward a solution, even though it's still not solved. We have a kind of framework for how you can approach the wave functions in this. So the Heisenberg chain is a really central model. It's just almost the simplest possible model. It's just a chain of spin 1/2s interacting through a dot product interaction, right? The Heisenberg interaction. So why does that give us lots of quantum mechanics? Well, a dot product interaction requires simultaneous satisfaction of x, y, and z components of spin. These components all don't commute with each other. So therefore, they induce quantum fluctuations directly. In many ways, this is what happens in the Kitaev thing as well. You have three mutually incompatible spin directions being asked to be addressed at the same time, therefore giving you a highly quantum state. So in neutron scattering, what you would do is you have your incident neutrons come in. They will scatter, changing energy and momentum directly with the quantum magnet. We will collect these in a detector. We'll reconstruct what all our processes were, and we will know what the particle production process was, right? We will know the features and energy momentum of the states that we can create. So what we've done is we've come at the neutron and we've actually created quasi-particles, in this case, spin-ons that you heard about. So we will be directly making spin-ons in the material and seeing their energy and momentum. So if you look at this here, this is a really interesting plot. So it's got this shape here. It's got a strong lower boundary. It's got this shape here, which is kind of, if you know about antiferromagnetism, this should strike you as weird, right? This is actually really strange, because this upper boundary of the continuum does not have the periodicity of the underlying antiferromagnetism. Right? And you can map these boundaries just onto two particles with sinusoidal dispersion relations, and for two particle production, you'll get them in here. But to get them over just this bit and not extending out to here, you have to put an extra condition in that these can only be created within half of a Brillouin zone. And this is related to these topological type things that Gabor was talking about earlier, but they're directly seen in the scattering. So actually from the scattering, we can interpret a lot about the nature of these excitations, that this is an excitation spectrum for spin 1/2 spin-ons, fractionalization, but in one dimension. It's harder when we get into 2 dimensions, just because the constraints in 1D for how we partition momentum and energy is much simpler, so it's easier to interpret. But that's what we can do. And here the material has got copper in it, and these coppers are coupled together by fluorines. And so it's a very, very good, this material is a very good example of a Heisenberg chain. We could do other things like Fourier transform the data. I won't go into this in too much depth, but essentially we can also Fourier transform the data, and it will have, you can then see the light cone of the spin-ons of them moving. So we can see the light cone. And there's also this kind of strange repetitive features up here with no scattering on every second site. This repetitive feature comes from the Van Hove singularity here, but the missing correlations is, again, something really important. We can visualize this data in terms of pairs of spin-ons being created and separating in time. And it tells us, when we have this missing signal, it tells us that there's no overlap between the original wave function and this intervening part of the wave function is the spin-on separate. So in this case, what you've got is what's called quantum scrambling, right? So you've got a new intervening wave function being created in between. So we can interpret the data using physical concepts, and then we have to relate it to the actual theory to be sure of what's actually going on. So we go through a process where we'll try and reason as much as possible around the data, but then engage with theory and modeling to see if we can actually get a direct match of what's going on. So there are, in the case of neutron scattering, in certain materials classes or certain Hamiltonian classes, we have got theorems that allow us to say, if we have a match between the theory and experiment, that exactly tells us the quantum state and the Hamiltonian of the material, right? So in many cases, neutron scattering is a complete data set. It is one that you can absolutely tell what's going on from it. The big problem is trying to relate the actual measurement to the underlying quantum states, which you probably got a sense from Gabor's talk that that's not a trivial thing at all, right? That's a highly non-trivial thing. Now, another thing that we need to understand is the idea of quantum critical scaling. So here's again our Heisenberg chain and how it behaves with temperature. If we move a system from one quantum phase to another at t equals 0, we will go through a quantum phase transition, right? And you get very typical behavior actually occurs at a quantum phase transition. If we have a second order quantum phase transition, the actual nature of the quantum state there will become self-similar. So you get self-similarity in the quantum state. You'll get extremely highly entangled state forming. And one of the consequences of this is we can see actually in data itself, if we have that kind of state nearby, or we're going through it, is we will see the self-similarity reflected in measurements like neutron scattering by the fact that you'll get things like energy temperature scaling. If we take our data and we correct for temperature, we just divide the energy by temperature, the actual different data sets will fall onto universal curves, right? So there is universality in a lot of quantum systems when they go, when they're very close to quantum phase transitions. And this will be important for us because all of these things provide us with diagnostics, right? So quantum field theories, which are essential in building up this picture of how quantum spin liquids behave, are very important for us when we consider understanding experimental data itself. But there's a caveat with it. Quantum field theories are extremely powerful, but they apply on continua, not lattices. All the physical systems we will deal with are lattices. And so one of the difficulties we have is often quantum field theories, although they're very useful for understanding the underlying physics, they can be difficult for us to use in actual application because they often apply at asymptotically low temperatures. But one case that dramatically shows the power of quantum field theory is the transfer sizing model. You've been taught that, the transfer sizing model during the course? I saw Chetan doing it on his tutorial the other day. Okay, so the transfer sizing model, I don't know what Chetan covered, but we can realize exactly this experimentally. And this shows you how experiment and theory can interact. And actually, in this experiment, we can drive this material, cobalt niobium, through a quantum phase transition. And we can see this quantum critical scaling. But we also observed a set of modes very close by experimentally, right? So we saw this experimentally. But there was a theory that had been done by Zamolodchikov that had actually predicted that you could get a kind of emergent E8 symmetry related to this quantum phase transition that would be reflected in bound modes. And that was exactly what we had seen. So extremely subtle quantum physics is actually observable in our experiments. So we observed, there's this paper came out soon afterwards, did a 1D magnet detect a 248-dimensional Lie algebra. And the answer is, of course, yes. That is exactly what we saw with these bound modes, which I thought was quite cool. So this, yep. Hmm? 240. Well, it's the ultimate symmetry allowed in mathematics. It is the ultimate. E8 is the ultimate symmetry. Lie group. Yeah. So that was quite remarkable. In a really simple magnetic system, you cool it down, you put a magnetic field on, it does something no one's ever seen in the universe before, right? So you can stick one of these things on a spectrometer, you can see something really kind of cool. So 248-dimensional. That's why it was significant. So they were still in the process of working out the whole Lie group. Okay, so I told you that one of the key things is field theory is fantastic, but for linking to experiment, we are always facing this difficulty that we're in fact dealing with the lattice. Now, I should say one thing that I think is really important here. In one dimension, the field theories survive to higher energies and higher temperatures than they do in our 2D spin liquids. So the fact that we are dealing with a lattice is actually more, presents us with a lot more difficulties in 2D in our spin liquid work than it will in 1D. So there have been really powerful methodologies at tensor network computations that have come along that can calculate the full S of Q and omega. They can do it really well. This is DMRG, density matrix renormalization group. So methods like matrix product states can actually quantitatively describe our data. In 1D at least. So I'd like to make a connection now that, you know, where we're at. So here's where we're at kind of in quantum physics, and it's kind of shocking in a way. It's nearly 100 years since Heisenberg proposed the spin-a-half chain model, and, you know, virtually everyone of significance in the last 100 years has worked on this model, or many of the most significant theoretical physicists. The surprising thing is it's not solved, and there's still big discoveries being made. And one of the big things that's been discovered is that you know, the actual transport of heat and spin through the system is non-equilibrium. It's out of equilibrium. It doesn't settle down. This system doesn't really have a temperature. And it falls into an out of equilibrium quantum universality class. That was a shocking thing when it was realized that this was a possibility. An experiment showed it was in fact correct. So it was due to the fact that it was discovered a second infinite set of conservation laws theoretically. And this is the implication of it. Now, the reason I wanted to bring that up is this is making a connection with quantum simulators and quantum computers. So for the first time, quantum simulators are providing us with complementary and useful information on these systems that we're looking at. And there was a recent paper in Science in April that came out by Thomas Prosen, who came up with this whole argument about that effective and quantum universality classes, where Google and Thomas had worked together, and actually they showed that this is not exactly the Candar-Parisi-Zhang quantum universality class. It's a new quantum out of equilibrium universality class. So this is an example where quantum computers are really starting to help us and connect with the experiment as well. Okay, now I'm going to go on to the spin liquids. And I'm going to go through our favorite spin liquid. I don't know if it's our favorite spin liquid, Gabor. it's triangular one. It's the classic spin liquid. Okay, we'll call it the classic, which is the triangular one, which came from Anderson's original proposal of resonating valence bond, where we'll have pairs of spin-ons, and you heard from Gabor about how we'll get these. And so for us, the visons will be kind of invisible, but the spin-ons are visible. Right, so in a nearest neighbor spin a half triangular magnet, it gets 120 degrees order. It orders, it doesn't form a spin liquid. But if you put further neighbor coupling, and if you get another exchange coupling, which we can get from tuning materials, where you also get another coupling, it's small extra couplings, you will put it into a quantum spin liquid state. Yeah. So, and we have materials that you can walk potentially over in terms of chemical composition that actually systematically will change this next nearest neighbor coupling. Okay, so in fact, that's great because, as we, yeah. Oh, that's where you're getting it. The system is more critical, so therefore it has longer range singlets. And that is actually pertinent to what we will see, because what we're going to do is going to see that these materials, this is a quantum phase transition here, and this material here will be really close to quantum critical. So in fact, it will have a lot of longer range quantum singlets. Yeah. So actually, there's a huge range of triangular materials available, and so there's a vast range of possibilities for tuning and so on. We can't currently predict the materials that well, but we're getting much, much better at it. Okay, so what's our key question? We've got loads of materials here. We've got lots of candidates, but if we want to start making a device, it's really difficult, right? That's a hugely more work than actually originally, just like screening and making sense of the materials. So our fundamental problem that we have is, how can we make sense of the quantum properties of material? How can we certify we're seeing what we want to see? And that's not a trivial question, because as Gabor's shown you, a lot of the physics is going to be hidden to a measurement. So one thing that we have a problem with is we can't just look at continua and say, I have a quantum spin liquid, because actually disorder can produce continua that look kind of similar, right? So we haven't got surety about what we're actually looking at. So in the Quantum Science Center, we actually use multiple criteria to, in fact, screen and identify whether we have quantum behavior that's at least suitable for us to move that across and start trying out devices with it. And we do this by using model-agnostic quantum entanglement witnesses. So that's borrowing approaches from quantum information theory. We use Hamiltonian determination, where we actually measure the parameters in the model, and we validate behavior with theory as well. So quantum information theory is something that hasn't really been applied much to these measurements, but it's something which provides a kind of deep mine of potential ways we can relate measurement and quantum states together. Why do we care about this? Well, I told you earlier that field theory is not powerful enough for us to use in our data. It has this continuum approximation. That means we can't compare our data sets with it. Things like tensor network, and we haven't got quantum computers are powerful enough to do the level of fidelity we need to actually know what we're looking at. So we're looking for model agnostic approaches that can take measurement itself, and we can understand nature of quantum systems from. And so we can use the same idea as you would use in a Bell's type measurement, where you have two photons that are entangled. By having different polarization settings, you can do what's called a witness experiment, where above a certain summation of the measurements, it's classically impossible to get that result, implying it has to be entangled. And this is a kind of what's called a witness type experiment. And these play a role similar to order parameters in condensed matter that we can use for identifying changes in materials or really pertinent aspects of it. And so we have an analog between this kind of thing. When we do our neutron experiment, we're going to come in with a quantum wave. We're going to interfere over different distances and times, And so we're actually measuring all kinds of information on these correlation functions, because we're getting full X, Y, Z information in each of the spin correlations, right? So we have this big mine of loads and loads of correlation functions we can put together in different ways and make deductions about entanglement. And in fact, there's 3 very powerful ones that we're using just now. There's actually a lot more that we've extended this to. One tangle is really important. The one tangle relates Bragg scattering essentially in the material, or lack of it, directly to the amount of entanglement between any spin in the system and the rest of the system, right? So it gives us a way of telling whether all our spins in our system are in fact fully entangled or not, right? And there's a theorem. The theorem's only valid at t=0, but it is a rigorous theorem. Concurrence and two-tangle, as is similar to qubit concurrence measurements. And that tells us the pairwise entanglement between spins. And then we can also use a trick from quantum metrology called quantum Fisher information. Quantum Fisher information is related to the accuracy you can measure something at. And you have a thing called the Kramers-Rao bound, the quantum Kramers-Rao bound, which relates the accuracy to which you can measure something through to the entanglement depth of the system. The more entangled it is, the more accurate you can measure it. So by having a strongly entangled system, you can go beyond classical limits in detection. We can kind of invert this so that the spin measurements that we do, we can convert that into quantum Fisher information, and actually you can then get your entanglement depth out of the system. In fact, you get a lower boundary on the amount of entanglement. The big caveat here is this sees local entanglement. It doesn't see long-range topological entanglement. So you can have all this other entanglement there. You can't see it with any local probe. You need to do a measurement where you braid these things currently, or perhaps we can do it with entangled particles. We're not sure yet. Okay, so here's a scattering from our triangular antiferromagnet, potassium and terbium diselenide. And these are the 2-spin-on scattering, basically. This is the multi-spin-on scattering. It's highly dispersive scattering. This is the 2-dimensional plane. These are cuts through it. This is along a wave vector direction. And this is an energy up here. And this is going down in temperature. It gets sharper and sharper till it's really sharp boundaries to it. So this is the scattering from the spin-ons that Gabor was talking about. And we can do these entanglement measurements as well. And we can identify, in fact, we have quite a lot of entanglement in the system. The system actually has more quantum entanglement depth in it than we expect for a spin liquid. In fact, this material is not a spin liquid. It orders at 300 millikelvin, right? So potassium and terbium diselenide is not a quantum spin liquid, but it's nearly a quantum spin liquid. We can tell that because the entanglement depth is high and it shows omega T scaling. So I told you that omega T scaling, energy temperature scaling, is the signature. You're very, very close to a quantum phase transition. And we know we're on the ordered side because we see a bit of order at 300 millikelvin. But we can go further. We can put magnetic fields on and we could change the quantum state of the system. In the case of a triangular magnet, you have a 1/3 magnetization plateau. And at this point here, it's not the spin-ons anymore. It's much simpler to solve. We have essentially magnons here. And so we can use measurements in this region to, in fact, directly extract our model parameters, because that one is solvable with perturbation theory. And so that's exactly what's done. When you take the actual parameters out, this is what the tensor network DMRG calculations look like. This is the data. This is actually a parton, a Schwinger boson calculation as well. So what we see, the spin excitation continuum looks an awful lot like it's expected to be. So we've validated that with theory. So we saw quantum criticality, meaning that we're really close to this transition. And we're seeing that it's almost a quantum spin liquid. We're seeing the spin-ons, but at very low energies and long distances, long distance and times, those spin-ons are confined. They're going to get pulled back together due to the magnetic order. Because if you have magnetic order, these kind of strings that Gabor was talking about that would connect anything, as you trace out the spin-ons that have been created, they separate, they will mismatch against the ordered spin, and therefore you will have a linear confining potential. It's just like asymptotic freedom, and so they'll stick back together. So a new technique that's being used now is neural quantum states. Here, that was used recently by our collaborators, and we actually identified that we know where this material is. It's at 0.045, and we know that the transition is now at 0.063. That's where J2 gets strong enough, you'll go into a quantum spin liquid state. So the material sodium ytterbium diselenide, we also measured the Hamiltonian, and we get that this is J2 upon J1, we get a 0.071. So it's, according to its Hamiltonian, should be on the QSL side, right? Now, it's not known exactly what the QSL is. We don't know what type it is. It could be a U1 direct quantum spin liquid, or it could be a Z2 quantum spin liquid. We don't know. But we see continua, we see no magnetic order, we see no confined spin-ons. This completely, our data all looks like a quantum spin liquid here, right? And one interesting point is, round about the M point here, there's still a gap. If it's a so-called U1 direct spin liquid, because of the continuous gauge symmetry, you actually get this goes gapless as well. For a Z2, that remains gapped. So we think this is actually a Z2 quantum spin liquid. Okay, so you do the comparison again with the MRG, and here's what we can state from the entanglement using our entanglement measures. We now see no order. So we have a one tangle of 1. Resonant valence bonds are expected to be 1. So it's very significantly entangled. The full spin is entangled. Two tangle, actually, two tangles not useful because you have a thing called quantum monogamy, which means that the singlets are all being shared amongst different sites. And the way that the Bell's inequality works is you have to see above a classical value. By sharing it, you've reduced that level. Even though it's fully quantum, you can't witness the pairwise entanglement anymore. Okay, and then entanglement depth, actually it's gone down, right? The entanglement depth is lower in this material. And that's exactly what you would expect to happen, because the potassium ytterbium diselenide is here. We have a quantum critical regime here. If our material is still on this side and closer, it is going to have much higher entanglement depth. It can only reduce its entanglement depth by going right over past this quantum critical regime, right? So you get maximum quantum entanglement depth in quantum critical regimes. And so that's told us we've stepped right over this quantum phase transition, and we're in the QSL side. Okay, so that's the evidence that we have a Hamiltonian that's within that. As I said, heat capacity is really important for all of this, and actually heat capacity is really difficult to calculate. It's really easy to measure, and it's really difficult to calculate. But this is using a typicality computation, and the heat capacity has been calculated for sodium ytterbium diselenide. And in fact, the heat capacity changes, and whether you're on the ordered side or the quantum spin liquid side of the quantum phase transition, and the experiment looks like actually exactly as what's expected on the quantum spin liquid side. Again, giving us further confirmation that we have a system which is essentially, it's working as a quantum spin liquid, and what we believe to be a Z2 quantum spin liquid. And this was a recent discovery here with magnetic susceptibility, is that there's a 26 millikelvin energy gap. And we think that's the energy gap for associated with the Z2 quantum spin liquid, or the quantum spin liquid formation. A lot more work needs to be done to look at this in detail. Neutrons can't go down to these energy scales. We have to push the technique. We're doing that now, but and that's what's always happening. We're always being challenged by the next thing we find out, and we're having to innovate with the techniques. Okay, so here we are. There's actually other materials that are now believed to be in this region, and we're now trying to understand the extremely low temperature behavior in the systems. And there's work being done, a lot of work in Quantum Science Center to actually be able to go from electronic structure calculations to the Hamiltonian, so we can systematically predict materials and choose the right ones for doing it. Right, here's my, Gabor gave you his way of thinking about the Kitaev quantum spin liquid. I'm going to give you mine, right? Because I don't think you'll get this from anyone else, right? Because this is how I figured. I mean, this is how I looked at it. I did a little calculation with my PhD student Anjana. So a lot of how the Kitaev spin liquid works is very special because it has a bunch of conservation laws in it. Now these have the effect of disassociating spins from each other. So if you, here's a trick that I would use that Gabor probably wouldn't use, but experiments, it's really useful doing the thing for a classical system as well as doing the quantum solution. So you will get an idea of what was a conservation law or a nonlinearity versus what was coming from quantum fluctuations. So something we always do. But if you get a classical Kitaev system and you do the dynamics on it, right? This is what it does. I'll see if I get this. Oh man, I don't know if it's doing anything. Oh, it isn't doing anything. It's a tragedy. But let me tell you what it does. Right. If you get a classical Kitaev spin liquid, it actually, the dynamics works that only 2 of the spin directions are actually dynamically active at any time, according to what the neighboring spin configurations are. So what in fact you get is essentially loops of spins which behave as one-dimensional systems in the system itself. There's one giant loop that goes right around the whole system, right? And that's your edge state. That's what can carry your edge currents and so on. But any of these loops, you can solve them with 1D physics, and that's essentially how you do the Kitaev model, because in fact, the Kitaev system is one-dimensional. It's made up for these one-dimensional subsystems. And of course, if you quantize these, they behave as spin-on pairs, right? So you can get some idea of how this stuff works more intuitively just from this simple model. What you'd have seen in the animation was that if you start shaking spins here and looking how they actually move, they will just, all the excitations are completely separated from other loops. It behaves as a pure one-dimensional loop, right? And that's why the Jordan-Wigner transformation essentially works in that. Okay, so do that, just run it, just write a short code or whatever and do it. I mean, I do it all the time to understand these things. But we do have, you can get Kitaev couplings. I won't go into details of how you get them, but essentially they're a higher order exchange to do with spin orbit couplings that you get between atoms. And the trick is when you're doing exchange, the super exchange, the normal super exchange is much more, the Heisenberg temperature is usually much stronger. But you can switch off by making the bond angle 90 degrees, which means there's not an orbital for the spins to both jump onto at the same time from the two spin 1/2 sites. And so they don't talk to each other through a Heisenberg interaction, and they pick up instead the spin orbit based interaction, and that's where you get Kitaev from. So you always need things that are like 90-degree bonds in the crystal structures and some spin orbit coupling. And this material ruthenium trichloride has these aspects. As you see in the neutron scattering, you get all these, you get continuous scattering. Actually, you get magnons in zero field, and you do see some sharp modes. But when you put the field on, it actually destabilizes the order, and it looks like a quantum spin liquid. That doesn't mean we understand it. It doesn't mean we know for sure it's a Kitaev quantum spin liquid, but it is not showing well-defined modes. So it's doing something really weird. I don't have time for talking about the transport and so on, but I would like to point out the following. In Kitaev models, although Kitaev models can have much bigger gaps than we can with the triangular systems, which make them in principle robust, they always will have lots of other couplings in them because we've switched off the 0th order coupling, and we're our KTF is in with a whole bunch of higher order coupling terms. So you're not going to get KTF alone. You're going to get these other ones coming in. So our models start looking horrendous. We think there's probably 10 to 12 Hamiltonian terms involved in the material. And we've worked up to 6 Hamiltonian terms, and we can't get an exact fit with the behavior yet. So this is getting to the state where it's extraordinarily difficult to do the physics, which is, so one of the solutions is, well, one thing is we want to do high field experiments to do the same kind of trick we did with the triangular lattice. However, we don't have these fields. This material has much higher exchange couplings than the triangular lattice, so we can't do that yet. But we can also instead do things like machine learning, AI, which allows you to do far more complex modeling. And that has been done up to 6 terms so far, and we have to move it up to 12 terms to try and get the match. We're seeing multiple matches of Hamiltonians at the moment. Actually, all the matches have a very substantial KTF term. So we do believe this has got KTF in it, but we don't know what the details are in the Hamiltonian. The other side of it is the thermal transport. There are reports of quantized thermal transport in this material. It does depend on the samples, and it's a very difficult material science problem and a difficult measurement problem. But this is a great candidate for actually doing the thermal flows, which Gabor has been alluded to in his devices. So these materials are at the stage where we're comfortable enough with them that it's time to actually, start making these things into something you can try out on the macro scale. So we will never know, I guess my final bit is we'll never know if we really have these long-range quantum states unless we braid them, unless Gabor comes up with a great idea how we can do it with our measurement. So that's it. It's a very complicated field. Our current status is we have a lot of approaches to it. We're making a lot of headway, but and it is absolutely a very close match between theory, experiment, materials, experimental technology, and computation. Okay, thank you very much.
Thanks everybody for the great discussions. Our next speaker is Rob Moore.
Great.
Here,
I'm finished.
National Lab. He's going to talk to us about the experimental side of topological superconductivity. Welcome, Rob.